All right, welcome to Pre-Calculus, and this is another video for Unit 1 over function properties. In this video, we're going to tackle the property of continuity. So continuity is a huge topic, especially moving into calculus, enormous topic. And it's all about basically being able to understand where is a function continuous. So first, let's talk about what the heck we mean by the continuity of a function. Graphically speaking, a function is continuous at a point if the graph does not come apart at that point. So this is a very loose, non-traditional, exact mathematical definition. So, what do we mean by how can the graph of a function come apart? What do we mean by come apart? So let's take a look at a couple examples. We're going to start with where a graph is continuous, meaning it's not coming apart. Then we'll look at some examples where the graph clearly comes apart. So here is a continuous function at x equals a. So notice what we have here on the x-axis is we're looking at this random variable or this random spot we're just calling a. Again, it could be 2, 3, 4, 5, 7. It could be whatever, you know what I mean? It could be any value. But at this particular value where x equals a, the graph is continuous. Now, there's a couple reasons why. One, there is a point right there. Right? We clearly see a point at f of a, right? When you plug a into the function, we do get a value out. And again, these number lines aren't labeled. I don't know if this is 1, 2, 3, 4, 5 or 2, 4. Who cares? The point is that there's clearly a point right there. We could see it, right? There it is, right there. Now, the other important part of this is if we study the behavior of the function f for x values close to any particular random real value a, we can be assured that f of x values will be very close to f of a. And right now, today, that might sound very confusing. Like, what is he talking about? So again, I have to understand that there is a lot that goes into proving that a function is continuous at a value a. Not only does there have to be a point there, but as we get closer and closer to the value a, so as we follow the function, getting closer and closer and closer to a, from either side, right? From either side, from above a or below a, as we get closer and closer and closer to a, the values of those values getting closer and closer to a are closer and closer to the value that we're actually at. And I know that I'm maybe not still doing a great job explaining that, so I'm going to keep going because I really want you to understand this hugely important concept. So let's just call the value f of a b. That means that there is clearly a point a comma b. When I plug in a to the function, I get out b. So a is on the x-axis, b is somewhere over here on the y-axis. So there clearly is a value a comma b, right? There is a point a comma b. But what if we are very, very, very close to a, but not quite there? If we would get really, really, really close to a, like maybe somewhere right around here, that value, its corresponding y value, needs to also be close to b. Obviously, it's not going to be b yet because it's close to it, but the point is it's really close. And on the other side of a as well, if I choose a value really, really, really close to a, but just slightly above, that corresponding y value needs to be really, really close to my b as well. So the point that I'm trying to make is that not only is there a value, a point at a, as we get closer and closer to a from the left and from the right, we're coming together to that point. So there's actually three things that are happening here. First, there is a point, right? You plug in a, you get b. There is a point at x equals a. But as we get closer and closer to a from the left, we're also getting closer and closer to that same b value. And likewise, as we get closer and closer from the right-hand side, we're also getting closer and closer to that b value. So all three things are coming together. There is a point at f of a. There is a value as we get closer and closer from the left, we're approaching that same value. As we get closer and closer from the right, we're approaching that same value. All those three things are happening, and that is why we are continuous at x equals a. And again, remember, this is the first time you're learning this, so it's not a surprise if it's a little bit confusing. Actually, when we start looking at some examples where we are not continuous, you will start to see how one of those three things fails. And as we learn more and more, into this year, we're going to be able to really define continuity a little bit better than I'm kind of loosey-goosey explaining it to you right now. But that's the point. We're just learning it for the first time. So I want it to be a little bit of new to you. There should be a little bit of questioning going on here, but I just want you to understand that three things have to happen. There needs to be a point at x equals a, and as we approach x equals a from either side, we need to be coming together at that point. Pretty simple. All right, so let's look at an example here. So here is an example, and maybe after this example, it'll really all make a lot of sense, but here's an example of a function that I'm telling you is continuous. It's actually continuous everywhere, but we'll get more to that later. Let's check x equals 5. I want to prove to you that this function is continuous at x equals 5. So the first thing I have to prove to you is that when I plug 5 into the function, I get a number out. I get a y coordinate out. So let's just check that. So 5 squared is 25. 25 plus 3 is 28. That means that there is clearly a point at 5, 28. Now, the next two things I have to check are where it's, again, new to you, a little bit weird. So let me explain. And to explain this, I'm actually going to use your calculator because the calculator makes this really nice. All right, so the first thing I want to do is actually want to type this equation in. So you're going to hit y equals x squared plus 3. All right, and then we can exit out of there. Now, one cool feature of your calculator that maybe you didn't know you had is you have the ability to evaluate values on your thing, right? So if I tell you to plug in 5, obviously you could do it in your head or you could do it on paper or pencil if you really need to, but your calculator is capable of doing this. So you're going to hit second. Oh, I take that back. I'm sorry. You're going to hit, not second, you're just going to hit vars. You're going to slide over to y vars, and you're going to go to number 1 function. Now remember, this is a list of all the different functions we had, and if you recall, a moment ago, I typed this function into y1 on my calculator. So I'm going to go and grab y1, and then I'm going to treat it just like you kind of see it on my screen. Next to the y1, I'm going to type in the 5. It's got to be in parentheses. So basically what I'm asking the calculator to do is take the number 5 and plug it into y. Plug it into y1 specifically because that's where I typed this function in. Hit enter, voila, we get 28. Okay, well, that was easy. We didn't need the calculator for that. But here's what we need the calculator for. The second and third items that I have to show that make the function continuous at x equals 5 is that as I get really, really, really close to 5, I'm also getting really, really, really close to 28. So I'm going to hit second enter. What that does is just pulls up the last thing I typed in. And I'm going to type in 4.9 because that's a number really, really close to 5, correct? And notice I'm pretty close to 28. Not exactly because I'm not at 5, I'm at 4.9, but I'm close to 28. And that's a good thing. But you know what? Let's get closer. Let's get really, really close to 5. And notice now I'm really, really, really close to 28. And this is what I was talking about with the graph a moment ago. As I approach 5, I'm also approaching 28. That's an awesome feature. That's an awesome characteristic of what it means to be continuous. But remember, you actually have to check both sides. So now I need to go to the other side of 5. So let me come back in here, and I'm going to delete all these values. Now, the other side of 5 would be like 5.01, 5.01, a number that is just to the right of 5. And notice that that number is also really, really, really close to 28. And in fact, if I go even closer, 5.000001, really, really close, notice that I'm, again, really, really, really close to 28. So what I'm proving is that, first off, there is a point at 5, 28. You plug in 5, you get 28. But what I'm also showing that makes continuity super important is that as I get really, really close to 5 from the left side, I'm also getting closer and closer to 28. And as I get closer to 5 from the right-hand side, I'm also getting closer to 28. And that's what makes this continuous. So how do we express those second and third things? So it's kind of weird, a little new notation here. We say as x gets closer to 5, now we have to signify that we're coming from the left. So we actually put a little negative sign right here. That little negative sign, that doesn't mean negative 5. That just means from the left. We put it a little above the 5 there. And then we say as x gets closer to 5 from the left, the function gets closer to 28. Now, it's not going to actually get to 28, but remember, it's getting really, really close, 27.99999. And then the other thing we say is as x gets closer to 5 from the right-hand side now, again, we put that little subscript plus sign, meaning from the right of 5, the function is also approaching 28. So not only is there a value at 5, as we approach 5 from both sides, we're going towards that same value. These are all sides that point to our function being continuous. Now, in a very elementary kind of kid way of talking about this, essentially what it means to be continuous is that you could draw the graph without lifting up your pen or pencil. That means you're continuous. It's a nice, smooth transition. Okay, that's what it means to be continuous. And you know what? The other thing you could do on your calculator is you could graph it, right? We already got it typed in there. We could do zoom 6, and we could see this nice, smooth graph, okay, where there was no places where the graph was out of whack, right? When we were graphing it, it was nice and smooth. And once again, now we're going to take a look at some non-continuous places, then this feature might make a lot more sense. All right, so here is what we call not being continuous, which is known as a discontinuity. Okay, now if we look at these two graphs, we see a problem at x equals a. And these are actually called removable discontinuities, and I'll explain where that comes from in one moment. But if you notice this, look what's happening here on this graph. At x equals a, there is a point. There it is right there, okay? And I could say that there's a b value there, right? So when I plugged in f of a, when I plugged a into f, I got a value. There is a point. It's right there. I squared it off. But something weird is going on there. Notice this now, and this is where you got to really understand. As I approach a from the left, if I get closer and closer to a from the left, I'm way up here. I'm up here at some different value. And as I approach a from the right side, I'm also, again, I'm up here at this different value. We actually call this a displaced point. I literally took a point that looked like it was supposed to be up here, and I just moved it. Well, that's obviously a discontinuity. You cannot draw this graph without without lifting up your pencil. You're going to draw it, and you say, oh, okay, I got to lift up my pencil, move the point down here, and then I continue to draw it. That's a discontinuity, and it's called a removable discontinuity because I literally removed a point and put it somewhere else. Here's another example with a slightly different twist. Here's f of a, or here's a, right? If I notice there is no point at f of a, so f of a does not exist. I mean, here, I took the point, like right here, I took the point, but I moved it. So there's still a point there. I just put it somewhere else. Here, I literally just threw the point away. It's called a hole. And that creates an issue. Again, to be continuous, there needs to be a point there. Well, I don't even have a point at A. And then again, as I move from the left, I'm up here somewhere. As I go from the right, I'm up here somewhere. So I am coming together. Like the left and the right sides of the graphs are coming together. But the problem is there's no point there. Remember, the three things that have to be true to be continuous is that there needs to be a point, and the two sides have to come together at that point. So in both of these graphs, that's not happening. The two sides are coming together, but on the left graph, the point was moved. On the right graph, I just threw it away. There is no point. So this is the problem, right? These two graphs are not continuous everywhere. Now, they are continuous at other places. So don't get me wrong. Like, let's talk about this value right here. I'll call it W, right? At W, I am continuous. There is a point at W. The left side and the right side come together at that point. Hence, I am continuous at W. Here's another value. I'll call it P. There is a point at P. There it is right there. The right side, the left side come together at that point. That's continuous. But at A, that doesn't happen. So in these two graphs, we are continuous everywhere except for A. Now, again, we can fix the discontinuity by defining the point of discontinuity. So again, now let's look at this graph on the right here. I could fix this if I filled in this point. If I said, all right, so instead of A being undefined, I'm going to define it to be that value. So if you could fill it in to fix the discontinuity, we call that removable discontinuity. I like to think of it as you took a point and you removed it. You either moved it somewhere else, like right here, or you literally threw it away. So that's important to understand the three different characteristics and how one of those characteristics fails in these graphs. Now, here's an example of this, and this is a rational function. You should have done a very big unit on rational functions in Algebra 2. So let's talk about what's happening in this graph and why, when you look at this graph, there is a removable discontinuity. Now, it's extremely difficult to see, but we're going to talk about it right now. All right, the first thing you should remember about rational functions is to factor both the numerators and the denominators. So on top, that's going to be x minus 3 times x plus 2. If you don't believe me, check my work, but that is the correct factoring of that. In the denominator, this is going to be a little bit of a tricky factoring one. Let's see if I can get this right. So it's going to be a 2x and a 2, not a 2 there, sorry, my fault. It's going to be a 2x and an x. That makes it 2x squared. Let's do 3 and 3 and see if this works. So let's see here. I want this one to be minus and this one to also be minus. Yeah, that should work. So I get a negative 6x on the outside and negative 3x on the inside. That makes the negative 9x in the middle. And negative 3 times negative 3 makes the plus 9 in the back. Okay, so there's the factoring. Now check this out. The x minus 3 on top and the x minus 3 on the bottom cancels out. That factor got removed. That's going to create a hole. Another reason why they're called removable discontinuities. So if I try to plug 3 into this equation, if I try to plug 3 in, you're going to get does not exist because 3 creates a 0 on the bottom and the top, and that's undefined. That just doesn't work. So that means that there is a hole at 3. Now, you're not going to see it in a graph. I mean, the whole, graphs have billions and billions of points, so you're not going to see one that got removed. But I'm telling you right now, in this graph, and again, you could zoom in on it with Desmos or something like that, but it's so tiny, you're probably never going to see it. But there is a hole right there. So the left side is coming together with the right side. I love it when the two sides come together like that, but there is a hole at 3. And again, if you don't believe me, plug 3 in and you're going to get 0. So that is the idea of why we understand that in this example, this rational function, there is a hole, hence the graph is not continuous. All right, let's talk about another type of discontinuity, and that is known as a jump discontinuity. Now, here is a discontinuity that's not removable. This is a different type of discontinuity. Here, what we see is that, let's go through the three things, right? If I said, all right, what's happening at A? Well, at A, there is a point. I could call it B right here. There is clearly a point B, right? At A, there is a point B right there. I can see it. Okay, but what happens as you approach from the left? What happens as X approaches B? Whoop, I take that back. It's supposed to be an A. We're always talking about the X value there. What's happening as X approaches A from the left? All right, as we approach A from the left, I am getting closer and closer to that same B value. So that's a good thing. So the function is approaching that B value. That's a good thing. But here's where we have an issue. Notice as I approach A from the right, I'm way up here somewhere. They're not connecting. So as X approaches A from the right-hand side, the function is approaching some other value up here. I guess you could call it C. So this is a jump discontinuity. So you have to understand, again, go back. There are three things that have to be met to be continuous. Number one, there's a point there. Okay, that works here. I like that. There's a point here. Number two, as we approach A from the left, we need to also be approaching that same value. Okay, that checks off. That's good. But here's where we fail. As we approach from the right side of A, our function is approaching some other value way up here. So there's like a gap in the graph, or we call it a jump discontinuity. This is much harder to fix. You can't fix this just by filling in a point, right? This is much more than just something got removed. There's a hole in the graph. That's not what's happening here. This is very different. So what we talk about, we're studying the behavior of the function as we get closer and closer to A. But we got to study it both ways, left and right. And the two sides, left and right, have to be coming together, and they have to be meeting at a point, and that's just not happening here. All right, this often happens in piecewise functions. We're going to do a whole topic on piecewise functions in a little bit, but you guys should understand basic piecewise functions. A piecewise function is a graph that's made up of two pieces. So here's an example of this. When x is less than 2, we're going to use a very simple linear function x plus 1, and you can actually see it here on the graph right there. But when x is greater than or equal to 2, we're going to use a parabola, which you can see right here. But the problem is the two graphs are joined at 2. 2 is where we switch, right? If x is less than 2, we use one graph. If x is greater than or equal to 2, we use the other graph. And the problem is at that switch point of 2, they're not coming together. So the first thing I'd say is let's check our three things. All right, what is f of 2? Well, if x equals 2, we're supposed to use this bottom equation right here. So we can plug 2 in. 2 squared is 4. 8 times 2 is 16, so 4 minus 16 plus 21. And you could use your calculator if you need to. 4 minus 16 plus 21 is 9. So we are up here at 9. Actually, you can see it right there. Nice and filled in dot. So the first qualification for being continuous checks off. But now we're going to say, all right, what happens as we approach 2 from the left? Approaching 2 from the left would be less than 2, and that's using this equation right here. And when I plug 2 in, 2 plus 1 is 3. That's why we see the graph stopping right here at 3. So that means from the left-hand side, the function is going towards 3. Okay, that's a problem because I need that to match up with where the function is actually at, which is 9. So there's an issue right there. And we could also check the other side of 2 from the right. And as we approach from the right side, we are going to that 9 value. So that's at least good, right? So here's where we have a jump discontinuity, right? One of the three things fails. So at 2, there is a point. 2, 9. We see a point right there. We're allowed to use 2, and we plug it into the bottom equation, we get 9. Awesome. But as we approach from the left, we're way down here at 3. That's not matching up. As we approach from the right, we're up here at 9. That's, again, it's not matching up. So that's where we have these issues of a discontinuity. But please, I hope you understand that we're good everywhere else. Let's, for example, 4. At 4, I see a point. Awesome. I'm approaching from the left side. I'm approaching from the right side. All three things are coming together. The left side, the right side, the point, they're all matching up. I'm continuous at 4. That's great. But at 2, I'm not continuous. So this is another graph where I'm continuous everywhere except for 2. All right, there's one more type of discontinuity, and it's called an infinite discontinuity. These graphs are not continuous, and they certainly cannot be plugged so that they're not removable as well. So as we study the behavior of the function f for x values close to x equals a, the values are infinitely high or low. So here are 3 different examples that can happen. So here's a function, and we're talking about 2. First off, at 2, I don't see anything. It does not exist. I don't see any points at 2. You know, it's actually a vertical asymptote. That means there's no points there. So that's the first issue. That's why I'm not continuous. But it's called an infinite discontinuity because as I consider the second thing, which is approaching from the left side, it looks like I'm going up forever and ever and ever. As I approach from the right, it looks like I'm going up forever and ever and ever. So those things need to be coming together, not going towards infinity. Infinity is not a number to be achieved. So that's infinite discontinuity. That doesn't meet any of my rules. Here's another one where we see at 2. Once again, there's no point. There's no point in 2. So right there's a problem. And as I approach from the left-hand side, I'm going down towards negative infinity. As I approach from the right-hand side, I'm going up towards positive infinity. So again, they're not coming together. A clear, big discontinuity. Now, here's another one that's very interesting. This is a really weird graph, but check it out. This is where we can really go over the 3 things you have to check. First off, wow, there is a point. If I plug in 2, there is a point. It looks like it's at 1. So 2, 1 is a point. That's a good thing. Check that off. As I approach 2 from the left side, I am getting closer to 1. Wow, okay, that's awesome. So check that off. That satisfies. But as I approach from the right-hand side, it looks like I'm going towards infinity. So once again, all three things are not happening. So let's review those three things, right? So first off, there is a point. If I plug in 2, I get 1. That checks off. The second thing, as x approaches 2 from the left, the function is approaching 1 as well. So 1 here and 1 here. This is awesome. Things are looking good. But then the last thing fails. As I approach 2 from the right-hand side, the function is going really up forever towards infinity, and all three things aren't matching up, and that's why we are discontinuous. Here's an example of that. I'm going to use my calculator again to show you guys this. It's pretty obvious, but I'll show you guys. So let's type this in first. So we're going to do 2x divided by, and then don't forget we got to use parentheses for the denominator, x plus 3. Okay, so let's go and exit out of here. And the first thing I'm going to do is remember vars, y vars, function, y1. I'm going to grab the function, and I'm going to say, hey, you know, I noticed this infinite discontinuity here. Hopefully you noticed it. It appears to be at -3. And I hope you guys remember from your units way back in Algebra 2 that just looking at this function, x is not allowed to be -3. That's going to create a vertical asymptote. But I just want to make sure you guys understand this whole idea of infinite discontinuity here. So when I try to plug in -3, first off, it says you can't do it. Divide by 0, impossible, can't do it. That's awesome. So we're like, yeah, okay, guess I can't do it. All right, but sorry, I hit the wrong button there. But what happens is we get really, really close to -3, right? So let's get really, really close to -3 from the left-hand side. -3, whoop. I used a minus instead of a negative. -3.0001. That's really, really close to 3 from the left. And look, I'm way up at 60,000. So from the left-hand side, the graph was going way up. Crazy, right? And then I can also check the right-hand side. If I do this again, vars, y vars, function, y1, -2.9999999. You know, just to the right. I'm approaching -3 from the right. I'm also, look at that number. That number's huge. I'm way down towards -infinity. So obviously, you know, all three things are not matching up. There's no point at -3. The left side's going up. The right side's going down. That is a discontinuity. Okay? All right. Now, this is a brand new topic. That's a really good one. I really want you guys to understand it. So let's take a look at a couple graphs first so we could see the different discontinuities. Let's identify all the discontinuities that you see in this graph. There's plenty of them. All right. The first one I see is at A. At A, there's an infinite discontinuity. So at A, there's an infinite discontinuity. The left side's going down towards infinity. The right side's going up towards infinity. And there's no point there. All right, let's talk about B. B is a jump discontinuity, or jump discontinuity, excuse me. Notice that there is a point at B. That's awesome, looks to be at 1, so there is a point. You know, if I plug B into this function, I'm going to get 1. The left-hand side is coming towards 1. That's a good thing, but the right-hand side is up here somewhere at like 1.5. They're not matching up. Clearly a discontinuity. Let's look here at 0 right in the middle. At 0, there is a point. So if I plug 0 in, there is a point up here at 1. Can't deny that. But check this out. The left-hand side, as I approach 0 from the left, shoots way down here to -2.5. And the right-hand side shoots way down here as well. So basically, this is removable. I took this point that looked like it was supposed to be right here, and I moved it up here. That's a removable discontinuity. And here's another discontinuity at C. Once again, there is a point at C. There's a clear point right here. It looks to be at -3, so that's a good thing. But the left side of 3 is way up here at 2.5. The right side of C is down here at 0. Well, everything's off at C, right? There's a bunch of crap happening that doesn't look good. So the left-hand side's way up, the right-hand side's down at 0, and the point is completely somewhere else. So that's actually a combination of a jump discontinuity and a removable discontinuity. A really weird one there. But again, don't forget about good points, well-behaved points. Like if I said, what about this value right here? Let's call it W. W, I'm continuous. There's a point right here at W. The left side is getting closer to that point. The right side is getting closer to that point. Everything seems to be happy. I am continuous at W. But I obviously have issues at A, B, and C, and 0 as well. So later on in this course, we're going to define what it means to be continuous a lot more officially than what I'm kind of saying now. But we have some stuff to learn first. But right now, the most important thing I want you to understand is visually, what does it mean for a graph to be not continuous and why at a particular point? All right, love you guys.